Thank you, Bruce. Hello, everyone. Very happy to be here, TIDES Europe, my first time. I've been in TIDES US for 20 years, and I'm glad I made it. So today, with my colleague Thomas from YMC Chromacon here in Switzerland, we will talk about some innovation and challenge and a bit of history of peptide manufacturing. Oh, sorry, this is the workshop. Our presentation is a bit more focused on preparative purification of synthetic peptide. My name is Marc Jacob, and I'm a chemist by training. So I actually was involved with peptide I would say in 2005, when I got hired by Bachem in Los Angeles, California, because there was a little peptide called hexenatide that was approved that year, and that's the reason I joined, let's say, the manufacturing of synthetic peptide. So I'm based in Los Angeles. I thought, being close to the ocean, I will stay there maybe. So a little history that you have seen in the presentation this morning from Bruce. If some of you were not here, peptides have been around since actually 1923. The human insulin was approved, and then now we are at 36 approved peptides in the last 10 years. So it's growing. It's going to reach $73 billion by 2030, and with the GLP-1, we're now at the ton scale of peptide manufacturing. So the process mass intensity has to be reduced. So the cost will go down and it'll be more sustainable. So, in case some of you are not familiar with the peptide manufacturing process, I would say it's 4 main areas. So the synthesis upstream, which a lot of work is currently done to improve the process mass intensity. A lot of talk on the liquid phase, but still nowadays, the solid phase peptide synthesis is the fastest, very, very powerful, very high purity. The coupling are virtually 99.99. Pretty amazing technology, so that can allow you to make peptide very, very quickly. Then you have, if it's done on solid phase, you have a cleavage step with a strong acid. Generally, it's TFA, but they are looking at other methodology, other acids. So hopefully there is some interesting talk on that topic in the next few years. Also, I'm at the TIDES advisory board, in USA, and we're always looking for good talk on peptide. And please feel free to send us your abstract. We would like to have some really good talk on the manufacturing. The purification step, which is what we're going to talk about today, it's mainly reverse phase HPLC, and I will do a little history of that technique. And then finally, the isolation can be a different way. We saw crystallization, but I will say spray drying seems to be quite interesting in my point of view. All right, so I'm a little younger, but not that much, of the reverse phase HPLC, who was first, Bruce Merrifield. We have to give him a little shout out, 1963. The solid phase peptide synthesis. So I put the timeline of some of the key peptide approved on the right, and then on the left, kind of the evolution of HPLC. So Horvath in Yale, combining with Waters, developed first bonded C18, and then the HPLC was invented. And then you have some early phase from DuPont, Waters, Vidac for peptide and protein. Vidac was actually in California, near Los Angeles. And then a small company was founded in 1971 with Peter Grog, but let's not forget Rao McEnany. They shake hands in Los Angeles, and McEnany started Bachem, California, and Peter Grog Bachem in Switzerland. And they were focusing more on long peptide in California and shorter peptide in Europe. Important the DAC was introduced, was patented, the dynamic axial compression, to pack the HPLC column at large scale by Roussel-Uclaf in 1974. Jean Rivière, a professor at the Schalk Institute, introduced some new additive for the purification, such as the triethylamine phosphate and then TFA as well. And then, let's go a little faster. The Prochrome commercialized in 1986 the DAC, and then for the first time, it was used in manufacturing by Eli Lilly in 1985. SMB was used for chiral separation, which is a technique of continuous processing. And then the peptides start to be developed, octreotide, goserelin. And then here we go, the 2000. The first large-scale purification of a peptide that was, let's say, a synthetic peptide was caspofungin by Merck in 2001. And then, of course, Roche developed the first hybrid process in 2003 in Colorado. And that was for AIDS, and the idea was they will need very large quantities. So they really revolutionized the way peptides were made, and it was more than 20 years ago. MCSGP was invented, but that we'll have a little explanation from my colleague, Thomas. And then, GMP peptide became, let's say, employed by many CDMO, and the scale were up to 100 kilo. And then further development in terms of stationary phase and, different bonding, YMC triad, which is a hybrid particle, was introduced for, a longer lifetime and regeneration of the resin, or purification at pH, up to 8, 9, even 10. So that's quite a significant advancement, I believe. And then in the 2020, we got the GLP-1, semaglutide approved for obesity, terzepatide, and MCSGP used for, process intensification, and then Albericio, which is here, maybe not here in the room, told us it's a golden age of peptide. And Dr. Eisenmuth from Bachem told us at TIDES USA that purification is not the bottleneck anymore. So, a little commercial. This is my company, YMC. So it's a global company. Our headquarters is in Kyoto, in Japan. I was just there last week. Yamamura, the founder, is here, and he really truly believes in continuous chromatography for the biopharmaceutical. And he's still at the helm. And our philosophy is to contribute to the scientific progress and the future of humanity. I think it's a good philosophy. So I'm based in Los Angeles. Here we go. So to purify peptide, you need a good analytical method to check the purity of your peptide, right? This is like your eyes. And generally, it's defined by the client. But back in the day, the CDMO will develop the method because they were much more advanced. So back in the day, when I was at Bachem, we will develop our analytical method. That's how I got excited about chromatography, being in Los Angeles, not far from a small company there that was doing some cool HPLC column. Your crude purity is critical. The related impurity and all these parameters that will affect your purification. And then you do some screening experiment if you have time. If you don't, you just take what you have and go for it. This is the fastest way to get a pure peptide. It's very easy when you are an organic chemist like me and you see that technology, you're like, oh my gosh, this is really cool to have that in your portfolio. And so you screen, you will see, I will show additive, phase, the critical loading experiment to improve your throughput. And then, if you are serious and you want to have an optimized process, you look at the lifetime and even regenerating your column to extend the purification of your process. Then you have the fraction analysis, which generally are a little bit shorter methods, so you can go a little bit faster in your purification. And the technology now is very high. It's UPLC. Back in the day, it was more 5 micron. Now we're like 1.7, 1.9. So it's very unfair, but it's good for the customer, for the end user. And then you go to a 5 centimeter column and you kind of optimize your process, make sure the parameters are good, and then you give it to the colleague or engineer, and they love it to scale that up. So in terms of the parameter, the stationary phase is very important, and that's what, my role at YMC is to be involved with the consumable, the stationary phase, and you have the C18, C8, C4. C18 has always been, it's like the vanilla of chromatography, but as the molecule get more, the peptide get longer, more hydrophobic, people have switched to C8. The pore size 100 angstrom is important because it gives you a high surface area, so you can potentially load more. But as the molecule gets bigger, if it doesn't go through the pore, then you have not necessarily an optimized process. So the 200 angstrom is becoming used a little bit more. And then 10 micron is the perfect combination because it gives you high efficiency, but a back pressure that can be handled by the DAC column. So 10, 15 micron, depending on if you use a 2 column or 1 column, maybe that's an option that you want to look at. And then, the way the silica, the particle size distribution is important, so that will affect also your performance when you pack the column. And then the column lifetime, like I said before, the chemical and mechanical stability is critical. And then the mobile phase, acetonitrile has been used, but if someone could come up with another solvent, that would be interesting, because acetonitrile is not necessarily the best. There is some talk about recycling acetonitrile this week. Then the additive, another area where I think a lot of improvement could be done. The amount of additive, peptide, have amino acid on the side chains, and so you can use this ion pairing to improve your chromatography, and the pH obviously is critical. And then the gradient. It's one of the cool things about peptide. Maybe the expert in chromatography can tell you why it works so well with peptide. And then the loading. You want to study how much you can load, because sometimes you have some unusual effect, like displacement effect, where by overloading your column, you actually get a better purification yield. So I have a case study here. It's not a very a new one that was approved in 2000, but it was one of the big peptide, large quantity were needed. Company called the drug was called Angiomax. So in this case, when it was developed, it's on a 5 micron analytical column. The purity was about 72%. So that's the analytical method used for release. So in terms of stationary phase, you can screen 5, and you had another C18, you can screen, I think, up to 16 now. There is some really nice equipment available, but I will say, at least 5 or 6. So that's the phase available from YMC. We have a 200 angstrom that's quite interesting for longer peptide. And then that's the mobile phase I was using back when I was making peptide. I don't know where we're at now, but I would love a talk on that from the experts, what the plus, the minus. But here you can go into a pH range, which give you that selectivity. By changing the pH, you change the selectivity of some impurity, and that can really help your purification. And you can go all the way to, I've heard 9.5. Peptides are stable until 9.5, so that gives you a nice range. And in that case, after doing the screening of phase, screening of the additive, and a little of loading, we were all the way to 1.5%, so it's by weight, so that's 35 milligram on a 250 millimeter ID column, which is about 2.4 gram of stationary phase, so it's about 1.5% loading, which is reasonable for a peptide with a purity of about 70%. And we were using ammonium acetate in this case at pH 5. There was a good, let's say, mobile phase for this peptide with that purity at flow rate of 1 ml. Sometimes people use a little less flow rate, but that's the recommended for the optimal efficiency. And then you collect the fraction. You know, you have your peak, you collect the fraction, you analyze the fraction, you define a pooling criteria. So we collect all the fraction greater than 98%. You can have a criteria for single impurity, you know, and then you have your final purity of your combined pool, you have your recovery, you have, let's say, for a phase one, that could be good enough. And so that's the first example. The second example, you know, I had to take the famous GLP-1. So we got the crude from one of our partners. A lot of people, you know, are already looking at terzipatide for, you know, become generic. So in that case, we screen 3 different solvents, pH, mobile phase, 2 solvent, acetonitrile ethanol, 4 YMC phase, and different loading. And so I was just in Japan last week, and I thought it was a good example, so I put it there for you today. So it's fresh from our lab in Kyoto. And so interesting, with TFA, it's very bad recovery. Maybe the peptide is not soluble very well. The peak shape is really ugly. And then at pH 6.6, we got the best result, about 3% load. We were going all the way to 3% load, so it's the one in the middle, and we were able to achieve 98% purity with a yield of 50%. If the purity of the pool is 93%, we could almost recover most of the peptide we load. Okay? So this is another example of a quick development. Now you have to tune up, you have to look at other phase, column lifetime, and maybe load more. Okay, so, and then when you have done that, that's actually a peptide I made. That was the first, manufacturing process. We had 80%. Maybe that was the first development synthesis. Then we developed the purification. So like that, you have a good, example. Your design space, is wide. And then we went back to the synthesis. We knew what was the impurity. And here we go. It was 99%. Maybe you don't even need chromatography, but yeah, we do a little desalting on columns just make sure everything is clean. I think maybe that's your old peptide, Bruce. It was an easy one, right? All right. And then, sorry, I have to be by the microphone, but I can't see very well. So, and then we use my favorite equation. So that's when the chemists meet the engineer. It's the diameter of the column, the analytical, to the prep column you're going to use. And it's based on pretty much you keep the length constant. That's why you pick 10 micron, you keep the length constant, and by increasing the ID, you increase the loading quite substantially. And you can increase, and you can scale up like that the volume of the sample, the flow rate, the load, everything is quite linear. And here is a little prep calculation sheet that I made for some of our customers. So if you load 5% on the 4.6 millimeter ID, you load 100 milligram, and then you can do an intermediate on a 50 millimeter ID, 12 gram, and then you just go to the 1 meter column and load 6 kilo. And then I'll pass on to my colleague. He's going to show you how you can make hundreds of kilo by using a semi-continuous process with MCHGP. And so, like I say, we have the resin, and now we're going to have the operational control. And Thomas will take the lead now. Thank you for your attention. I'll be here if you have any questions.
Okay. Yeah, thanks. Okay, can you hear me all well? Yeah, good. So, welcome also from my side. So, my name is Thomas Muller-Spath. I'm leading the group of continuous chromatography of YMC in Zurich, not far from here. And today I'd like to show you how continuous chromatography can help you solve some of the challenges that we see with peptides. And these challenges are especially amplified when we talk about GLP-1 peptides, because there we have larger amounts that are needed and more waste that is generated. So here you see on the left side a projection of the demand of peptide GLP-1 taken from a Novo Nordisk annual report. Showing that depending on the dosing regime, we have like tons of GLP-1 peptide needed per year. And also on the right-hand side, you can see the expected amount of waste that is to be generated depending on the dosing regime, which exceeds 2 million, whereas the amount of peptide that is required exceeds easily 100 tons. And this is without even the oral dosage form, so that will increase these amounts even by a factor of 10 or even 20. So as a pharma executive, then you start thinking probably, okay, so how do I manage this, right? So the market is expected to grow 50%. How can we produce all these amounts? The manufacturing capacity crunch is preventing us from gaining market share. Where do we get the staff to run this, right? How do we handle all the materials and waste? So these a lot of questions, which essentially can be boiled down to three challenges. One is the scale and capacity crunch, right? How do we produce those amounts? Then the second is how can we run it under GMP? Where do we find the staff also to run it and the resources? And the third one is the sustainability mandate that's related to the raw materials and waste. How can we handle all these tons of raw materials and waste? So in the last couple of years, MCSGP, which stands for multi-column countercurrent solvent gradient purification. So I'll explain how it works in a little bit in a couple of slides coming. So in the last couple of years, this technology has proven to be useful and to give some improvements over batch chromatography. So you see on the left-hand side, batch chromatography run with a 60 centimeter column produces like 3 times less than a process that uses MCSGP, which with an overall resin volume, which is just half of the batch column. So significant improvement in productivity. You can also see that on the right-hand side. This is taken from a case study that you can download on the Bachem website. And you can see on the right-hand side, the process time was reduced from 5 to 1 days, and the PMI, process mass intensity, which stands for the waste generation of the process, is also reduced by a factor of 3, from 5,700 kilos to 1,600. There's some knock-on effects also on the number of in-process controls on the lower left side, which can be reduced using this process, and also the lyophilization volume can be reduced, which can be also sometimes a bottleneck. So this process then has further been shown to improve also, or to be capable of producing amounts in the ton scale. So what you've been seen previously was less. Now we go into ton scale. Again, this is a case study shown by Bachem for bivalirudin, the peptide that Marc also mentioned. So here you can see on the right-hand side, we're getting to production of 50 to 90 kilograms per week. So if you think of that being scaled up to a year times 50, right, we end up above 2 tons and then going towards 4 to 5 tons, right? So definitely with MCSGP, also multi-ton scenarios are capable, are feasible, and this can debottleneck the downstream. It will create other bottlenecks potentially in the logistics and neighboring unit operations. So that has been shown, and MCSGP, I will explain how it leads to this debottlenecking. What is actually enabling this better performance and the savings in time? So one of the main things is that it reduces QC offer. The second thing is that it can operate 24/7, and actually I forgot the first thing. It eliminates rechromatography. So that's those are the most important points. So you can produce faster and more and lower manufacturing costs. So how does it work? A short intro. So MCSGP addresses this challenge that we face in preparative chromatography of peptides, which is called the yield purity trade-off. And this means that as soon as you load a substantial amount onto a column, you see overlaps of the product and the impurities, which means if you want to take a center cut, you have to go very narrow, and you get high purity, but you get low yield, right? Instead, if you widen the product fraction, you start to include impurities, you get a high yield. That comes at the cost of purity, right? So we want to be in the upper right corner, right? This is both of this is not good. So an MCSGP can actually get you there, right? So we get to the upper right corner, we stay above specification, we can get a high yield and high purity simultaneously, and this has many advantages. So how does MCSGP get us to the upper right corner? The main difference is the treatment of the side fractions. So in batch chromatography, when we have impure side fractions that you can see here on the left-hand side, they either have to be discarded or they have to be reloaded in some kind of rechromatography step. So they're collected and they're reprocessed later, which is a significant cut for the productivity of the overall process. So rechromatography is very bad for overall productivity. Now in MCSGP, we use 2 columns, and we run this chromatography on one of the columns, right? And whenever an overlapping fraction elutes from the first column, it is transferred to the second column. So this fraction of the chromatogram is staying inside the process, is not leaving the process, it's staying inside the process, and it is repurified automatically, right? So, and the product in this side fraction is recovered automatically. So no external rechromatography, and it can run fully automatic. So it also can run linear gradients, and you've seen it does a center cut purification. So a typical MCSGP chromatogram will look something like this. So you have elutions coming from the 2 columns, left column, right column, left column, right column, 1, 2, 1, 2. We take out product every elution, and also every elution, you see we take out the side fractions and we put them onto the next column. Then also feed is loaded onto the next column, and then the whole chromatogram is run again. So it continuously operates, it continuously produces product, and the feed continuously gets less. So it's, besides being continuous, using 2 columns, increasing the yield, it's good to know that it's applicable for a wide range of products. That includes not only peptides, but oligonucleotides also, or other modalities where you are running a linear gradient. And very importantly, we have using UV-based dynamic process control for robust production. So this I will explain on the following slides. This process control is called AutoPeak, and it essentially works like a collection by threshold that you know from single column batch chromatography. So instead of collecting at a fixed time or volume, we collect based on a UV threshold. So whenever the peak moves, the collection will adjust accordingly with the peak movement, right? So that's essentially how it works. And this then can compensate for changes that are caused by temperature variations or column bed height variations, or feed volume variations. So all of this can be compensated for using this technology. Okay, so just to give you an example for temperature fluctuation, this is a case study that has been published, and we have a first reference operation where we are not using this control. The design experiment, as we call it, it's okay, right? We're collecting in the back of the peak, good purity, good yield, 95, 95. So, but as soon as we increase the temperature, this is reverse phase chromatography, so retention is highly temperature dependent. As soon as we increase the temperature, the peak moves to the front, and the collection window is too far in the back of the peak. So we will not have high yield and high purity. Same if we lower the temperature, the peak moves to the back. So we are also losing our performance here. Now instead, with the AutoPeak control, the collection window is shifted. You can see that here. Here it's constant, it's always at the same time. Here it's moving together with the peak, and like this we can get high yield, high purity at the same time in all of those cases. So very important for robust operation. What is also important is the process design itself, right? So, and I'm going to show you here how we can design MCSGP for varying feed compositions. So on the left side, you see a chromatogram on the top where there's an impurity called W, and that same impurity now is present in a second feed material here in a much larger concentration, right? So, and we want to purify now these both crude materials with the same operating parameters. So if we choose our product collection window like this, that's okay for the top part, right? Let's call this an aggressive cutting strategy. It's okay for the top. We will get good purity there and good yield. But for the lower part, you can see we're starting to include these impurities here. And that's a problem, right? So we will possibly go out of spec here with this aggressive cutting strategy. Now instead, let's give it a second try with a different cutting strategy. Now we choose a narrower product window. We have, again, the same feeds as on the left side, but now we choose a narrower window. And you see, because it's narrower, we are not including these impurities here in the front, right? So, and in both cases, we get, with this conservative cutting strategy, a good purity and good yield. So we sacrifice a little bit of productivity, but the process is running 24/7 anyway, so that may be acceptable. But it's much more robust against feed variation. So good in both cases. And this well-designed process has been shown also to operate also like in real world, right? This is again a bivalirudin case from Bachem showing very good consistency of the process in case it's well developed, right? So you have here hundreds of slightly more than 100 elutions run, and elution 3 and elution 103 have exactly the same product profile. And yeah, so the process can work very stably over extended periods of time, and this is the system that's was shown also in the Bachem annual report. It's an operation in the Bubendorf site, not far from here. So with this cutting strategy, we also, with this conservative cutting strategy, can reduce the number of QC samples, and this contributes a lot to cost savings of MCSGP. So in the top part, you see a batch process campaign, where for every batch, 10 fractions are taken per elution to squeeze out the last bit of yield out of this process, right? Every fraction is analyzed. We see, is it still okay or not? If it's not okay, we have to go to the re-chromatography, right? Now, in MCSGP, what we can do is we can say, okay, we take a very conservative cut. So the product in this fraction will be in specification for sure, right? What is on the left and on the right-hand side is automatically recycled. So we can be very conservative, right? We give away a little bit of productivity, but that product in this fraction will be in spec for sure. Like this, then, we can say, okay, we just take a big pool for this product elution. So we can cut the number of samples by at least a factor of 10. This has also been shown, again, in the bivalirudin case, actually on the TIDES conference in San Diego earlier this year, where the number of in-process controls per kilogram of peptide was cut from 80 to 3. So more than 90% reduction in the number of IPCs for a similar resin volume. Okay, with this cutting strategy, we actually also enable green, what we call green MCSGP. So the background is this, that the industry is trying to move away from solvent systems that are toxic and contain forever chemicals like acetonitrile TFA. So TFA is a forever chemical accumulating in the environment. People try to replace it. And we have green solvent alternatives. However, these have drawbacks them too. So the batch process with acetonitrile TFA is established, right? We get a chromatogram. It has some overlaps of impurities. We can get a center fraction. We have to take some side fractions. But overall, it's decent yield, a few side fractions. It's okay, right? So, but it's not green, right? So instead now, if we go to a green process, let's say we use ethanol and acetic acid, for example, as counterigent, then we get worse resolution, right? So we get a chromatogram with much broader peaks. So this means that if we take a pure fraction, that fraction will be actually very narrow, and we have to take many side fractions because a lot of product is in side fractions that are not pure, right? So it will be green, but it has a bad yield and many side fractions. So in this chart up there, we will go to the lower left. The yield will go down, the productivity will go down. We have a green process at a worse performance. Now, let's give it a try with MCSGP, right? We use, again, green solvents, so we'll end up with the same bad chromatogram, right? But in this time now, because of the recycling feature of MCSGP, we can recover the product in the side fractions. So this means we can use the green solvents we get a good yield, we recover the product in the side fractions, and we have 0 side fractions for the rechromatography, right? So it's all done automatically. So this means that with this process, we can now go up in the upper right corner. So basically, it enables green chromatography here. So that already gets me to my summary. So I hope I could show you how MCSGP can help you address these following challenges: capacity crunch, resource automation challenge, sustainability, and how it can debottleneck peptide purifications. So it can be a part of your overall approach to come up with a robust process. We can do something here also on the process side. We have to do something with the feeds, with the resins and the columns, but on the process side, we can use continuous chromatography to help improve here. So thanks for attending. If you're interested in learning more about MCSGP, there are 2 further contributions. One is a poster presentation by AstraZeneca, and the second one is a talk by Bertrand Guillard from Novartis, which will be on Thursday afternoon. And of course, you can come talk to us at the booth and continue the discussion. Thank you very much.
Open it up for questions.
Thank you. Really nice presentation. And I have a question for both of you. You see here when you are doing the analytical part of before a purification process, that we use very small particle size, 1.7 and so on. But when you move to Prep HPLC, you have 20 or you have 15 and so on. So it looks like a gravel in comparison with the stuff, and you see these not very nice peaks on the Prep HPLC. Is there any limitation apart from back pressure? Is the end of, could we one day imagine a system who could have a resolution of an analytical column in a prep system and then apply this wonderful technology? Or is just a mechanical issue, it's just an engineer limitation? Can we imagine a future with really small particles in prep?
The question about back pressure and particle size, right? You cannot defeat physics, really. I mean, you'd have to improve the pore structure, which then will decrease the surface area, right? And then you will have less capacity, right? So the physics will give us some limitations here. But what for sure is the case is when you use larger particles, your resolution gets worse, your throughput gets better, your resolution gets worse. Similarly, like with the green solvents. Using this MCSGP process, you can use larger particles and increase your throughput. So it works without sacrificing the yield, you know. Yeah.
So the answer is we are limited by physics, back pressure.
Yeah.
So we cannot give this problem to an engineer to say, hey, go there and find a pump which is strong enough. It's not a matter of mechanics, it's a matter of the process itself.
Yeah.
You could go a little bit lower, like 7 micron, maybe 5, but 1.7, that would be challenging. And for like single guided RNA, where the quantity are less, you know, some certain molecule where you don't need ton scale, you could think about going 7, even 5, but you know, when you get bigger, the engineer have to do a little improvement on the instrumentation.
Thank you so much.
Also, the pressure issue will become very prominent when you go to large columns. You need very thick column sizes, right? You need a lot of steel. It becomes very heavy. It becomes impossible to handle, you know, to roll the thing. The column will be like 10 tons or something like that. So there's also these kind of constraints to it, yeah.
Excellent. Any other questions? All right. Oh, just one more.
Hi. Thank you for your presentation. Can we ask some questions about your MCSGP simulations?
Simulations?
Yeah.
Yeah, sure.
If there's any significant difference between the column 1 and the column 2 in the settings of the parameters?
Yeah, so depending on the simulation, that simulation may account for difference in column 1 or column 2, right? So in operations, you can also see there's a difference between the two columns, right? You've seen it here with the p-value case where we have kind of a zigzag pattern. Sorry, I need to go back here. Yeah, here you've seen it, right? The two columns are always a bit different. So depending on the simulation, you can account for it, but in the operation, you have to use the UV-based process control because the peak will always move a little bit. So, and then you can compare also the simulations with the experiment. Yeah.
Great. Let's thank Marc and Thomas again for a wonderful presentation.